All right, so previously we talked about ordinary points. Ordinary points are the ones where we were looking at the differential equation y double prime plus p of x y prime plus q of x y equals 0. Ordinary points are points where these two functions p and q have power series. And so if there's a power series centered at the point x naught, then we say x naught's an ordinary point of this differential equation. If it's not an ordinary point, it's called a singular point of that differential equation. And singular points come in two types. They come in regular and irregular, or non-regular. A regular singular point is one where P and Q don't have power series at this point, but it turns out they're not far from having a power series. So the power series method is still going to be kind of fixable in a certain sense. And then non-regular singular points are one where there's just no hope of the power series method ever working at that point. So we're not going to focus on the non-regular singular points, just the regular singular points. So what I want to do is I want to share with you a theorem, and this is a theorem due to a mathematician named Frobenius. Okay, and so this is now what's called the Frobenius method of solving these differential equations using power series. So first, let me tell you the theorem. And the idea is that we're going to start with a regular singular point, and it turns out that there will be certain power series. So it turns out that if x equals x naught is a regular singular point, so if it's a regular singular point of that differential equation, y double prime plus p of x y prime plus q of x y equals 0, then we can get a power series solution. So then the ordinary differential equation has at least one solution, possibly more, but there's always going to be at least one solution of the form, so of the following. So of the form y is x minus x naught times r times the normal power series. Now, I want to point out that r does not need to be an integer, and in general it will not be. And therefore, this is not really a power series anymore. This is a times, by the way, that's in front. So you're multiplying this power series. So this series legitimately is a power series. When you multiply by something with a non-integer exponent, it's no longer a power series, it's just a series. So power series are kind of like generalizations of polynomials, but as soon as you have that fractional exponent, it's not a polynomial, it's not a power series anymore. So that's the difference. What we're going to do is I want to walk through an example of finding a power series solution. Okay, so I want to walk through and I want to solve, I want to find the solution to 3xy double prime plus y prime minus y equals 0. And we can quickly write this as, y double prime plus 1 over 3x y prime minus 1 over 3x times y equals 0, so that our p of x and actually our q of x are basically the same. So p of x is 1 over 3x, and where q of x is negative 1 over 3x. And I just want to point out that 0 is a singular point because we're going to have a problem with power series centered at 0, but it's a regular singular point because if I look at x minus 0 times p of x, you end up with 1/3. And if I look at x squared, so x minus 0 quantity squared times q of x, you're going to end up with negative x over 3. And these are both of those functions are analytic, in other words, have power series at x equals 0. So that means that the method of Frobenius is going to work just fine. Okay, so we're going to be able to take this and we're going to be able to find a power series solution we're going to be able to find a power series solution according to this theorem of Frobenius. So let's do this. Let's just jump in. So we're going to look at, we're going to try and find, we're going to, let's say, set y. We're going to find a solution, a series solution of the form x to the r, c sub n, x to the n, as n goes from 0 to infinity. I'm going to move the x to the r inside, and so this is going to be the sum from n equals 0 to infinity, c sub n, x to the n plus r. And there's going to be one subtlety here when we're finding y prime and y double prime. And if I just want to take a step back here, if we're talking about just power series, x, let's say y is this power series, c sub n, x to the n, when you differentiate, remember that this means c0 plus c1x plus c2x squared, and so on. When you differentiate, you're going to lose the constant term, okay, because it's a constant. However, that is not the case anymore, okay? That is not the case for us, because these are no longer going to be constant terms. When n is equal to 0, you get c sub 0, x to the r. And if r is not 0, then this is not going to be a constant term. And so the way that that's going to manifest itself, the reason why that matters, is that when you differentiate, you need to actually leave the starting index the same. Okay, so this is going to be the sum of, if I just differentiate using the power rule, we're going to have the sum from n equals 0 to infinity, c sub n, so that's a c sub n, times the quantity n plus r, x to the n plus r minus 1. Okay, so that's y prime, and so that's y prime, and y double prime is going to be also the sum starting at 0 of c sub n, n plus r, times n plus r minus 1, x to the n plus r minus 2. Okay, so all of our series actually start at the same value, n equals 0. And now what we're going to do is we're going to take these values for y, y prime, and y double prime, and we're going to plug those back into y, y prime, and y double prime in our differential equation. So our ODE, our differential equation, is going to become, let's see, we're going to have y double prime. I'm going to have to write a little bit smaller here, but we have y double prime, so c sub n, n plus r minus 1, x to the n plus r minus 2, so plus 1 over 3x times sum from n equals 0 to infinity of y prime, so that's c sub n times the quantity n plus r, x to the n plus r minus 1, minus 1 over 3x times the sum from n equals 0 to infinity, c sub n, x to the n plus r. That's all going to be equal to 0. Okay, and now this is the monster that we have to deal with right now. So this is our series solution. I don't want to say power series, but it is a series. Okay, so this is our series solution. And what we're going to have to do is just combine the terms, do all of the, try to mimic all the usual tricks that we can, and see what happens, see what we get for solutions. So the first thing that we can do if we want, it's really kind of up to you how you want to handle all of this, but yeah, the first thing we can do is just multiply all three parts of this by 3x. So we're kind of undoing the work that we did previously. And because I'm going to be so short on space, what I'm going to do is I'm going to multiply all the terms by 3x and then simplify all in one step. So this left side is going to be the sum from 0 to infinity of 3 c sub n, n plus r minus 1, x to the n plus r minus 1, because we multiplied by 3x. So if I multiply by 3x, that puts a 3 here, and that adds 1 to the exponent of x. And then the other terms I'm just going to copy, but without the 3x being divided by in front. So this is going to be plus the sum from n equals 0 to infinity, c sub n plus r, x to the n plus r minus 1, and minus the sum c sub n x to the n plus r. Okay, from n equals 0 to infinity. And that should all be equal to 0. And there's going to be a few other things that we can do here, but one other trick that we can just exploit, one thing that we have at our disposal is I'm going to factor out, and I actually could have done this at any point, but I'm going to factor out an x to the r from all these terms. Okay, so x to the r. So we have x to the r, x to the r, x to the r, and that's going to help us. That's going to help us just kind of look at what's going to, what we're going to have to do next. So x to the r, excuse me. So x to the r, if we factor it out, we're going to be left with this whole sum, n equals 0 to infinity, 3 c sub n plus r times n plus r minus 1, x to the n minus 1, plus the sum from n equals 0 to infinity, c sub n plus r, x to the n minus 1, minus the sum from n equals 0 to infinity, c sub n, x to the n equals 0. And now, despite there being r's inside the brackets here, so despite there being r's inside the brackets, we're going to basically treat this like a normal series. Okay, it's not exactly a normal series. Okay, again, because we have kind of it's not a power series, but it is a series, and so we'll do the usual tricks. Okay, and so for the usual tricks, we can do a few things. What we can do is, so what I want to do first is I want to write, this is really just a matter of convenience and a matter of preference, but what I want to do first is I'm going to take these first two sums, so the two leftmost sums, and I'm going to combine them. I can just combine them. I have the same powers of x and the same starting index. Everything's fine if we combine them. So we're going to end up with 3 c sub n. So this will be the sum, by the way, from n equals 0 to infinity. We get 3 c sub n times the quantity n plus r times n plus r minus 1 plus c sub n times the quantity n plus r. That's all times x to the n minus 1. And then minus the other sum, which we haven't messed with, n equals 0 to infinity, c sub n x to the n. And that should all be equal to 0. And let's see, from here what we're going to do is we're going to look at a few things. So we want, let's look at our starting indices here. So when n is equal to 0, this is going to give us x to the negative 1. And when n is equal to 0, we'll get a constant term. So I'm going to peel off the n equals 0 term on the left sum. And also I want to point out that I'm going to keep writing it just for consistency, but you don't really need to keep writing this x to the r term. If I have x to the r times something being 0, I know that the only way that that can happen is if the thing after the x to the r, the thing in the brackets, is 0. So you don't really need to keep writing it. I'm going to keep writing it out of convenience. But, okay, so we're going to go over and we're going to plug in n equals 0 into this term. And when we do that, we're going to see that we have 3 c sub 0 times r minus 1 plus c0 times r. After we peel that out, we're going to be left with the sum as n goes from 1 to infinity, 3 c sub n. Actually, let's also combine. I'm doing, I think, too many steps at once for the first one. So let me actually break up. I was tempted to do two steps there, but let me actually just do one step at a time. So before we pull out the n equals 0 term, what I want to do, as silly as this is, it'll just save us a little bit of time. So I want to factor from under in that coefficient. I'm going to factor out. Notice that we have a c sub n and an n plus r. And then we're left with 3 times n plus r minus 1 plus 1. Okay, so that's what we're left with there, x to the n minus 1. All right, and now let's factor out, the n equals 0 term on the left. So when we do that, when we factor out the n equals 0 term, we're left with c0 times r times, let's see, if n is 0, we're left with the quantity 3r minus 3 plus 1, so 3r minus 2, and then plus the other part, so the sum from n equals 1 to infinity of c sub n plus r times, this is going to be 3n plus 3r minus 3 plus 1 x to the n minus 1, and then plus the other sum, which we have not touched in a few steps now. Okay, final thing we're going to do is in this sum, we're going to shift the index, which is why we peeled off that term before. So this is, let's copy this. This is c sub 0 times r times 3r minus 2 plus, well, if we want to have this sum starting at 0, that means that we're going to change all the n's to n plus 1's. So this is going to be c sub n plus 1. This is going to be n plus 1 plus r. This is going to be 3 times n plus 1 plus 3r minus 2 plus the sum from n equals 0 to infinity c sub n x to the n. And what this means is that we're going to be able to now combine everything. And we got a lot of information here. We know that on the left we can combine these two sums. So the sum from n equals 0 to infinity. This is going to be, oops, and I forgot our x to the n here. I forgot our x to the n there. This is going to be c sub n plus 1 times the quantity n plus r plus 1 times, so this is going to be 3n plus 3r plus 3 minus 2. So 3n plus 3r plus 1 x to the n plus c sub n all times x to the n. So I did 2 steps at once there. I simplified our sum ind, the thing inside the sum, and then I combine these two because they have the same starting index and the same power of x. So everything's fine. And all right, now we're ready to see what this is going to do for us. We're going to have, again, we can ignore, we don't really need this x to the r term anymore, but we got a few things that we know. I'm thinking of this right-hand side as a sum, but actually I get a little bit more information than maybe we were expecting. We get that c naught times r times 3r minus 2 has to be 0, because there's no term on the right side, so that means that that has to be 0. And what that means is that either r is 0 or r is 2/3. Technically, there's a third case. It could be that c naught is 0, but if I were to take that value and plug it into this recurrence, that would just tell us that we get y equals 0 as a solution, which we already knew. So we don't actually get anything new from c naught being 0, so we don't need to worry about it. So this tells us that we're going to have two solutions, or two indices, r equals 0 and r equals 2/3. I should point out that this is what's called an indicial equation. So it's an equation, that equation is called an indicial equation. It's the equation concerning the indices, okay, concerning our values of r. So now what we need to do is we need to think about what's going to happen in both cases. And in either case, let's just look at this sum being equal to 0. And what that means is that we must have that c sub n times n plus r plus 1 times 3n plus 3r plus 1 plus cn is equal to 0 for all n greater than or equal to 0. Okay, so that's our other equation that we get from that equality, right? That's our other relationship that we have. That's the recurrence. And let's just study this first if r is equal to 0. If r is equal to 0, then our recurrence is going to become c sub n plus 1 times n plus 1 times 3n plus 1 plus c sub n is 0. In other words, the recurrence is going to be that c sub n, and this is true for all n greater than or equal to 0. So c sub n plus 1 is going to be minus c sub n over n plus 1 times 3n plus 1. And so that tells us that if c naught is a, right? So if c naught is a, then let's see what's going to happen. We're going to get that c1, when n is equal to 0, we're going to get that c1 is equal to minus c naught over 1 times. So if n is 0, this is 1 times 1. So that's minus a. And c2 is going to be, let's see, minus c1 over 2 times, so if n is 1, we get 2 times 4. So that's going to be, we end up with minus 1/8 c1, which is minus a. So that's going to be a over 8. C3, I'm just going to go up to c4 here. So c3 is going to be minus c2 over, if n is equal to 2, then we're going to get that this is, so if n is 2, this is going to be 3 times 7. And so we're going to end up with negative 1 over 21 times a over 8. And that's going to be, let's see, negative 1 over 162a. And maybe one more. I might need my calculator here. So c4 is going to be minus c3 over, let's see, if n is equal to 3, we're going to end up with 4 times 10. So negative c3 over 40. So that's negative 1 over 40 times c3, where c3 was negative 1 over 162. A, so that's going to be positive. Let's see, 4 times 162 is going to be 648, so that's 6480 A. So that tells us that one of our solutions, is going to be given by this sum. So it's going to be given by x to the r, c sub n, x to the n equals 0 to infinity. R was 0, so this x to the r is just going to be a 1. And so this really just works out to c naught plus c1x, c2x squared, c3x cubed, and so on, with these values of c naught. So this is going to be a minus ax plus a over 8 x squared minus 1 over 162a x cubed plus 1 over 6480a x to the 4th, and so on. And if you, again, want to get in the habit of factoring out the a, there's going to be 1 minus x plus 1 over 8x squared minus 1 over 162 x cubed, and so on. All right, 1 over 6480 x to the 4th. All right, so there's one solution. And that was all a solution that we got from r equals 0. We had another solution in our indicial equation, and that was r equals 2/3. Okay, so r equals 2/3. If r is equal to 2/3, I want to think about what does that tell us about our recurrence. So let's copy down our recurrence, just because I don't want to have to keep scrolling back and forth. So let's copy that. Okay, so our recurrence was there. So if I plug in r as 2/3, we're going to end up with c sub n plus 1 times the quantity n plus 2/3 plus 1 times the quantity, let's see, 3n plus 3r is going to be 2 plus 1 plus c sub n equals 0. And let's see, if I have, this just happens to work out nicely, if I have c sub n plus 1, this is n plus 5/3, but then this is 3n plus 3. So in other words, that's 3 times the quantity n plus 1. And so what I'm going to do is I'm going to take this 3 and distribute it in the parentheses to the left. So I'm going to left distribute that because then we can get rid of the fraction, which I think everybody will be in favor of. So we get 3n plus 5 times the quantity n plus 1 plus c sub n equals 0. And finally, what we're going to do then is solve this recurrence. So we know that c sub n plus 1 is going to be equal to minus c sub n over the quantity n plus 1 times 3n plus 5. And this is going to be true for n greater than or equal to 0. Just like before, and for the same reasons as before, we can let c naught be whatever constant we want. Just so that there's no confusion, I'm going to let c naught be some value b, right, rather than some constant a, but just pick whatever you want, I don't care. And what we're going to do then is we're going to figure out what we get here. So remember that this was for r equals 2/3, and c naught was b. So let's first figure out what exactly are our constants c1, c2, c3, and so on going to be. And I'm just going to find up to c3 here because these numbers get a little bit, they grow quite big, very, very fast. So the denominators grow very big, very fast, I mean. And so what we're going to get is, let's see, c1 is going to be minus c naught over, let's see, we get c1 by plugging in n equals 0. And so if we plug in n equals 0 to the denominators there, we're going to get 1 times 5. So we're going to get minus 1 over 5b for c1. And c2 is going to be minus c1 over, let's see, if n is equal to 1, we're going to get 2 times 8 is 16. So this is going to be minus 1 over 16 times c1, which we said was negative 1 over 5b. Altogether, that's 1 over 80b. c3 is going to be minus c2. Let's see, if n is equal to 2, we're going to end up with 3 times 11 in the denominator. So it's going to be 33. So this is going to be negative 1 over 33 times 1 over 80b. And let's see, 80 times 3 is going to be, so 3 times 80, just to explain what I'm thinking here, 3 times 80 is going to be 240 plus 2400. I guess technically I'm doing 80 times 33 is the way I'm thinking about this. But this is 240 plus 2400. So that'll be 2640. And that's negative 1 over 2640b. Okay, I'm not going to do C4. You can do that on your own if you want. But anyways, so now that means that our solution that we're going to get, remember that this was all for the indicial value r equals 2/3. So our solution is going to be y equals x to the 2/3 times our sum as n goes from 0 to infinity, c sub n x to the n. So that's x to the 2/3 times c0 plus c1x plus c2x squared plus c3x cubed and so on. And then we're going to sub in our actual values. We get that this is x to the 2/3 times b plus, let's see, c1 is going to be minus 1/5 b, that's x. c2 is going to be 1 over 80 b x squared. C3 is going to be minus 1 over 2640 b x cubed, and so on. And then I'm going to do two things all at once here. I'm going to factor out the b's, which we're used to. Okay, so we're going to end up with b. And then I'm going to actually, I'm going to factor out the b's, and I'm going to distribute in the x to the 2/3. This is, again, no longer a power series, but it is a series solution. So we're going to get x to the 2/3 minus 1/5 x to the 5/3 plus 1/80. X to the, let's see, 2 plus 2/3 is 8/3 minus 1/2640. X to the, let's see, that's 9/3 plus 2/3, so 11/3. Okay, and so on. And there's our series solution. And we found two, in this case we got lucky, and we found two series solutions to our differential equation. So that's 1. So that's b times x to the 2/3 minus 1/5 x to the 5/3, and so on. The other solution was this one here. Right? A times a quantity 1 minus x plus 1/8x squared. This one genuinely is a power series, okay, because you have all these, the powers being non-negative integers, right? X to the 0, x to the 1, x squared, x cubed, and so on. So that really is a genuine power series solution. Here, this is not a power series solution, but a series solution. And that's how that works. Okay, so let's just very quickly at the end combine our answers. So the general solution to this differential equation, so the general solution, our general solution is going to be, I'm going to call it y. So it's going to be y is a times the function that we had, right? It was 1, I already forgot it here, minus x. So it's 1 minus x plus 1/8 x squared minus 1/162 x cubed, and so on, plus b times x to the 2/3 minus 1/5 x to the 5/3 plus 1/80 x to the 8/3, and so on. Okay, so that's the general solution to our differential equation.